So I am going to do this presentation in English, I understand. See? That is good, because my Spanish, I know one word, cerveza. I will try to go very slow and try to enunciate my words so you are able to understand. To start, I would like to thank the university for inviting us here to present. I would also like to thank Carlos Cruz, who is here in the front row, for making all the arrangements to bring us down. Traveling with myself is Seth Florin, who is the president of my company, and Tom Merrifield. Tom Merrifield, who will speak tomorrow, mañana, I know another Spanish word, on particulates. But to get started, let's move on to the next slide. So as an introduction, to give you an idea, background of what I do and what our company does. The name of our company is Consolidated Analytical Systems. As you can see from the slide, we provide expertise in the design, manufacturing, integration, and support of monitoring systems for ambient air, industrial fence line, and natural gas sectors of the industry. What this means, what we really do, is we build air monitoring shelters to house the instrumentation. We utilize different instruments from different companies. You've probably heard of Thermo, Fisher Scientific, or Teledyne, API. We take all these different instruments from different manufacturers, put them inside a system, and then we provide a complete air monitoring system. And we can measure anything from criteria gas pollutants, which we refer to as SO2, NO2, CO, ozone, lots of your gases that you would measure for pollutants in the ambient air. We can also measure particulate matter. We can do PM10, PM2.5, total suspended particulate, and then we get into measuring VOCs. VOCs, benzene, toluene, ethylbenzene, xylenes. You've probably heard some of these in some of your classes. So that's kind of what we do and what our company does. I have 17 years experience in this industry. I started in soil and groundwater, and now I'm doing ambient air. Today, I'm going to walk around a little bit. Today we're going to talk about what the regulatory driver is. So in the United States, this is the US EPA. So the US EPA comes out with regulations. They tell us they tell each local, state, and federal government what they need to measure. We're going to talk about what are volatile organic compounds, VOCs. Hopefully you've heard some of these terms. I'm not sure what you guys' level of experience is as far as what classes you've taken and what your knowledge base is, but we'll go through it very slow. We're going to talk about how we are exposed to VOCs. We'll talk about health and the environmental impacts of VOCs. We'll talk about where do they come from, what causes VOCs. We'll talk about how to sample VOCs. We'll talk about the measurement process, and then at the end we'll have questions. And if I did okay with my slow English, you will have lots of questions. Okay, so to begin, we were talking, when I said what we would talk about, I talked about the regulatory drivers. That is the US EPA for the United States, the US EPA Clean Air Act. That act was passed in 1970, and then it was amended again in 1990. It is the basis for the U.S. National Air Pollution Control. It started before 1970. The Department of Health was concerned about the environment, but really there was no regulation to control the environment. So before 1970 in the United States, the air was very dirty, very particulate laden, very hard to see through the air. Once the Clean Air Act was passed and different industry was forced to control what was coming out of the smokestack, the air has gotten much cleaner. And that also goes with particulate gases, VOCs, as we talked about a little bit in the beginning. So the Clean Air Act was created in order to protect human health and the environment from adverse effects attributed to polluted air. This slide just shows a little bit about, it's pretty much the front page of the Code of Federal, what we call the Code of Federal Regulations. These books are all about this thick and there's a whole bunch of them. You don't ever want to read them, very boring. But specifically, CFR 40 is the environmental book. So it's a book very thick and it covers all the environmental regulations for the United States. Parts 50, 53, and 57 deal specifically with air quality. That's the ones that we're concerned about for this discussion and also what our company is concerned. Okay, so what are volatile organic compounds? There's a specific rule or specific, I guess, section of the US EPA that they call air toxics. They are also known as hazardous air pollutants. What these are is, like some examples when I touched on them earlier, benzene, toluene, xylenes, perchloroethylene. Perchloroethylene is like what they use, what dry cleaners use. So when dry cleaners use to clean your clothes, perchloroethylene. Then there's also metals, arsenic, mercury, lead, etc. All of these things can cause cancer or other serious health effects. That's why we're very concerned about VOCs in the air. Okay, how are we exposed? So how does this get inside our body? Obviously, breathing contaminated air. You breathe it in, it gets into your lungs, it goes into your bloodstream. Eating contaminated food products from animals. So if you have a cow in a field that is contaminated with mercury or lead, it gets into the cow's system. Then we eat the cow, it gets into our system. Also fish. Fish are very well known to pick up pollutants very easy. So when the water is contaminated, fish get that into their bloodstream. You eat contaminated fish, it gets into your bloodstream. Drinking contaminated water, ingesting contaminated soil, so eating soil, you get dirt on your hands, you eat food with dirt on your hands, it gets into your system. Touching contaminated soil, dust, water. This talks about swimming. So if you're swimming in a lake that has been contaminated with some sort of pollutant, you have the potential to get the pollutant inside of your body. Once toxic air pollutants enter the body, some pollutants can accumulate in the body tissues. So they can accumulate in the fatty tissues, the lungs. It's just a bad thing. Cerveza. That's going to be my go-to word. Okay. So health and environmental effects of air toxics. As I said before, health. You get an increased risk of cancer. It will damage the immune system, damage the neurological system, reduce fertility, In some certain areas where there's been high pollution concentrations, there's actually been studies shown where the fertility has gone down. Developmental problems, so children, when they're very young and they are exposed to toxic air pollution, they have developmental problems. Their brain doesn't develop like it should, they don't grow. And also respiratory problems. I know just talking to Tom Merrifield, he's been going to Beijing, China, to educate the government of Beijing on particulate matter in the air. Every time he comes back, he has a respiratory infection. Even wearing a mask, he comes back, he has to get antibiotics for respiratory infection. And he's actually going to talk to you tomorrow about particulate. The environment. VOCs have a direct impact on the environment by aiding in the formation of ground level ozone. Everybody thinks of the ozone layer way up in the sky. It protects us from UV rays and protects the environment. Ozone on the ground is very bad. It's very bad for your health. So VOCs actually cause they help aid ground level ozone to form. So where do they come from? Where do we get VOCs? Where do VOCs come from? Mobile sources. Everybody can see this. Cars, trucks, buses. You drive down the road and you see the exhaust, the black smoke coming out of the car or the bus. Stationary sources. Factories, you see the smokestacks. You can see these. You see the smokestack. You see the smoke coming out of the stack. Refineries, power plants, it's all visual. You can see the pollution in the air. Indoor sources, building materials, cleaning solvents. You cannot see those, but you can smell them. If you ever used a powerful cleaning solvent, you can smell. The smell is the VOC. Uncontrolled release and biogenic sources. Obviously, you guys are very familiar with volcanoes. If you see a volcano erupt, it will give off harmful VOCs. You'll smell the H2S in the air, the rotten egg smell. That's also one of the gases that will be emitted from a volcanic eruption. So how do we measure for VOCs? We know this is all in the air. We know it's bad. Now we want to measure it to make sure that the levels are safe for the human body. In the United States, we set up ambient air monitoring networks. The networks, the two that I have here mentioned, deal directly with VOCs. So one that we have, we call the Photochemical Assessment Monitoring Stations. We call it PAMS for short. So this is a set of instruments around the United States. There are 58 stations throughout the United States measuring just ozone, oxides of nitrogen, and VOCs. And these are mainly concerned with what I talked about in the last slide, the formation of ground level ozone. We also have an entire air toxics monitoring network. And these measure specifically just the hazardous air pollutants. So, as I just stated, the US EPA requires that federal, state, or local governments monitor the ambient air at multiple locations throughout the United States so that at any time, anybody actually, you could log on to airnow.gov in the United States and it will tell you what the air quality is wherever you live. It'll tell you it's safe to go outside today, or it will say the elderly and small children should stay inside. The air is too bad for them to breathe. As an example, this is actually an air monitoring station that we built in Birmingham, Alabama. This station specifically measures ozone and particulate. If you see the samplers on top, the ones that are around the outside of the railing up there, those are all filter-based samples. So they pull in air every day, they collect it on a filter, a small little filter. That filter is then sent to a lab for analysis, and they'll tell you how much particulate was in the air that day. The one in the middle, that is actually measuring continuous particulate. So it's pulling in air, and it's consistently providing data, continuous. So it'll give you data, you can look at it every minute and you'll see new data. This is another example of a monitoring station. And this one's in Nashville, Tennessee, but this is measuring completely different. This one measures NO2, nitrogen dioxide, CO, carbon monoxide, and it's also, so that's the only two constituents that this system is monitoring currently. So on top you see NO2, below that CO, below that you have a data logger that collects all the data from the instruments, and then it also pushes it out to that website. So it tells you, it's constantly updating and telling you what the air quality is in that location. So at this point, we're going to talk about some common means to measure VOCs. How do we measure VOCs? At this point, I'm going to turn it over to Seth Florin, who is the president and also our engineering manager of the company. He has probably over 17, 20 years experience building systems specifically to measure gases and VOCs. He's an expert. His Spanish is not as good as mine. I know two words, C and cerveza. He only knows cerveza. But he will be able to answer all your questions at the end. So, Seth?
Well, thank you for having me. It's an honor to get to travel outside the United States and present to groups, everyone from educational institutions to regulatory bodies to facilities that want to set up new monitoring networks. I wanted to add on real quick to some things Tom was talking about with the US EPA regulations and sort of how they approach these monitoring networks. Specifically, Tom spoke about the photochemical assessment monitoring stations. I wanted to touch base on this prior to going in, because what we're seeing is a revision of these stations in the US. And the reasoning behind this is because technology is our driver. Technology allows us to measure better at lower detection limits in real time. And as we progress with building new technology and to refining existing technology, we can then look at our regulations and we can make those better for the environment and better for public health, which in the end will give us a more representative, a better understanding of what it is we have in the ambient air and what we can do to resolve those issues, or as we say, mitigate those issues. One example with the photochemical assessment is for years, I don't know if this thing has a laser pointer on it, we were using these, and these are just canister samplers. They're 6 liters in size, and they're collected through very basic pieces of equipment. All this equipment does is regulate flow, and it's a timer. It says when for a valve to open, when that valve's supposed to close. That was really the best technology because we needed the laboratory. We needed the precision that the laboratory could give us to give us data that we were sure was accurate, and that data would be defensible. That way we could say, yes, we're for sure this is what's come out of that facility. Well, what we've seen, and this is about the past 10 years, is our ability to go to continuous monitoring. So this monitoring is now putting the laboratory into the field. And what we can do is we're able to then generate more data. We're able to trend during the day much better. And we're able to provide a more accurate reading. We can provide better detection limits actually in the field. EPA at the moment is redoing this regulation. I believe this is the first time since the early 90s they've had a look at this photochemical assessment monitoring stations. And they're undergoing a huge task where they've invited 8 separate groups of vendors in to do field evaluation and field testing and proof of concept. And what this is going to do in the end is it's really going to supplement that data. It's going to supplement our canisters and that high-end equipment that we keep in our laboratories, our GCs, our GCFIDs, our GC mass spectrometers. And we're going to have a better idea of really what is in the ambient air. So I'm going to go ahead and kick off here. Common means to measure VOCs. Yeah, pointed over there. First, we're going to talk about active or passive sampling. Basically, when I say active or passive sampling, I'm referring to sampling that is done in the field and then transported to a laboratory. The laboratory will then analyze those samples and provide us the concentrations of those samples. These samples are typically collected into a treated stainless steel cylinder. These are very common in the US. Or we use different types of materials. Polyurethane foam. Or we'll use a media-based sampling tube, something like a 10X or a carbon derivative that we're able to pull sample gas over and to capture those VOCs onto there. The second part, we're going to talk about continuous sampling. And basically what this is the GC in the field. We're going to talk about instrumentation that collects and analyzes samples continuously and provides real-time data, or as close to real-time data as possible. We're going to start here with our first technology for measuring these VOCs. And this is active sampling. What we're doing is we're taking one of these 6-liter canisters or a 1-liter canister, and we're hooking it up to a device. And that device will control flow rates into the cans. It's going to control our sampling time. It may even begin to fill a canister when the wind is coming across a facility. And that facility is known to have specific VOCs that could affect the population. There's many different reasons behind why and when we sample. And we'll touch base on this a bit more near the end of the presentation and the conclusions. But basically, we collect ambient air samples into coated or chemically treated stainless steel canisters that is sent to a lab for analysis. This is very important. Some VOCs are very reactive. And we know that if you have a metal canister, that metal may have iron in it. That metal may have a compound that's adhered to it. And what will happen is the VOC can react. And either you can lose the VOC or the reaction can cause another VOC to occur inside of the canister. This is very important to understand, especially when you're measuring near a facility and you need to know what is coming off of that facility. The second part of this that's extremely important is knowing what is in the air. We want to make sure that with these canisters, we don't take samples on extremely high humidity days or possibly have a high ozone reading and say 100 parts per billion. These can cause chemistry to occur as that canister is traveling from your sampling site to the laboratory for analysis. These are all things that we must keep into account when we're talking about this. The time of sampling is user defined through the use of a regulator. So basically, there's a small regulator, and this says in 6 liters of volume, I want to fill the volume of that sphere in 1 hour. So basically, I set it at 6 liters an hour for my flow rate into the canister. Commonly, we run these samplers for 24 hours in the US when looking at ambient air, not next to a facility, but just wanting to look at the general air. we'll sample for 24 hours, and we sample every 3 days, every 6 days, or every 12 days. And that depends on where the sampler is located. And finally, the sample is analyzed off-site. So when we sample, we need to know what compounds, what analytes we're looking for. And we're going to pack up this canister. We're going to make sure that there's no leaks. We're going to fill out our we say chain of custody, the paperwork that says where the sample is from, the ID number of the sample, maybe something specific that it was a high wind event, make a note. And then we're going to send that information with that to the lab for analysis. And critically, we're going to tell the lab, I want you to look at a method. In the US, we would say method T015, T015. Or we could say we would like for you to do a VTEX analysis only. So we need to let the lab know so they can narrow down and look only for the compounds of concern. This can make your data better, more precise. Secondly, the second technology. This is as basic a technology as we get to in the industry. This is true passive sampling. When I say passive, we're not affecting anything with the sample except the start time and the stop time. So what we do is, this is just an example of one. Inside of this sampler, it is hinged. It opens up. There is a disc about that big that's contained, and it's made of polyurethane foam. It's very not standard polyurethane foam, very pure, clean polyurethane foam. It sits inside of the device. The device can be connected onto a street lamp. It can be connected onto a tree. It can be connected onto the side of this building. And very simply, it allows the air to flow through the device, onto the polyurethane foam, and then out of the device. We allow that to happen, sometimes for 30 days, 60 days. And then we will pick up the filter, and once again, we will send it to a laboratory for analysis. The nice thing is, these samples can give a lot of information. They can be very easily deployed. And they're typically for the long-term sampling, like I said. The interesting thing about this is there was a study, and the study was done by a gentleman out of Canada. And he had these samplers running in, I believe it was 120 countries. And they exposed the filters at the exact same time. So the entire globe sampled at the same time. And that's one of the big, it's one of the good factors about this, that these samplers can be deployed, and with a good plan, they can really tell you a lot of data for low cost. So we'll just touch on the benefits quickly on the active passive. So the benefits, they're easily deployable. They don't take a lot of power to run. They maybe no power at all. They can be connected at near an industrial source, near a factory, to do a collection of the sampler, or they can be put in very pristine areas. They can be placed in a national park. They can be placed on borders, and that way you can get long-term evaluations. They are low cost. These can go typically from a few hundred US dollars per analysis for either the canister or the polyurethane foam in this case. And it's also cheap to buy the samplers. They're not very expensive. They can be very basic in the way they operate. So they've got lots of upside to these. They provide what I say is a snapshot, just a short-term view of the conditions that are there during the sampling. That snapshot can allow you to have this as your first step towards setting a permanent monitor or deploying additional resources or people to do this type of monitoring. But there is a downside. The downside, I say integrated sampling. And what I mean by this is we're collecting this sample and we're collecting it over a large amount of time. And by doing this, when we look at the data, we have data that may be one data point for 24 hours, so one day. Or we have a data point that's for 30 days. It doesn't tell us if these compounds were being quickly exposed onto the population or if it's a very consistent level of VOC. And this is important when you look at public health. You want to know if someone is exposed for a short amount of time to a high concentration VOC, or are they exposed to a lower concentration for a longer time? Depending on the VOC, it truly matters. Sometimes short-term exposure at high concentration is not as bad as long-term exposure at low concentration. Also, if you're wanting to use these for analysis and to look at a facility, if they're having an uncontrolled release or they have an equipment malfunction, when you take that sample, it can take 3 to 5 days before you have a result. If the facility has a problem controlling VOCs, or they have a tank that is leaking, a storage tank that maybe has a chemical in it, you may not know for quite an amount of time that you're having high exposures to these compounds. You have reactivity inside the canister in the case of the active sampler. We may have sample loss. I've seen where samples have been shipped and they've sat, and the method states that you must analyze within 15 days for some, 30 days for other compounds. I've seen a loss of 20 to 30% in specific compounds due to reactivity in the gas itself. So just the gas reacting with other molecules and other compounds that are present in that gas. And then just a small one is power may be required, and that is for the active sampler that controls the canister. If you have electrical timers, this is something to think about. With the other device, there's no power ever required. The second technology, this was a step. So we went from measuring compounds onto the substrate of polyurethane foam in our small salad bowl looking sampler. And what we've done now is we've adapted it onto an accepted environmental measurement platform, which was the high volume air sampler. This was really one of the first automated samplers that was ever developed. And it was developed back in the 1950s. And basically, it's a blower motor. It's just a small motor that pulls air in, a timer, and a totalizer that just tells us how long we've run for. And on the top, we'll set our device in that we're using to sample onto. Now this device started out as being just a piece of quartz paper. And that quartz paper just pulled in the air, and particulate or dust would settle onto that filter or be collected onto that filter. We would then weigh it. Well, what we found is over the years, we have other needs, and they've adapted this to other platforms. But for this, it's important to know the polyurethane foam sampling. And this is the same. The question was, what is worse for human health? What produces the VOCs, or I guess how we come in contact with it? I think the worst thing is not knowing. Just not knowing what's there. Because many people don't have the best understanding. The easiest, however, is to look at facilities, because we know what is there. Facilities, roadways, large population areas, basically large cities, and then moving out into more rural areas without as many people, without as many pollutants. So not knowing is the worst for me, because there's so many things that can be easily corrected for not a lot of money and very simple changes. But from their facilities, roadways, large areas of population and people, and then rural areas is how, when I'm asked, I start with networks. All right, thank you all. It's been a pleasure. An honor to be here and speaking with you. So thank you very much for your time. Except now we're pulling air onto this filter. So what we do is we pull air into the device. This lid is closed. The air comes up through and down into over our puff, over our polyurethane foam. The foam collects the VOCs onto it for whatever amount of time it runs. I mentioned the sampler contains a pump, timer, and flow control. And these are typically deployed for transport or fence line monitoring. These are very good to run next to facilities that we know may have a need for these measurements to occur. They're small. They give us a very high volume of air. And this is very important because with passive before, we need a lot of days to get those VOCs on it. Using this type of device, we pull the air and we pull the VOC on to the polyurethane foam. And we collect it. We force those VOCs to get into our equipment. So in a much shorter amount of time, we're going to be able to get a much higher mass of VOC collected onto that foam. But once again, we're now taking that foam out, we're putting it into our sample collection vessel, we're filling out our paperwork, and we're sending it away to our lab. So once again, this is not on site. The benefits. It is easily deployable. These are very simple units. They don't take a lot of concrete. They don't take a lot of electric to run. And they can be placed and moved quickly. We have a moderate initial cost to deploy. We have to have power at the site. It is required all the time for these. They're too large to run off of the motors are too powerful to run off alternative energy sources in most cases, or it will become cost prohibitive. Cost will not allow you to do that. The big, go back forward, sorry. High surface area to absorb the VOCs. The polyurethane foam is porous. So as you pull down, it's not a solid. It actually comes down through, similar to carbon. And it allows the VOCs to entrain or to adhere to that foam in many different places. So those VOCs are more apt to collect on that type of media rather than just a subsequent air sample. And we also have high flow rates. We can get a lot of air over these filters in a short amount of time. And that amount of air is critical to collecting enough VOCs that we can then analyze in the laboratory. Downsides. Once again, this is integrated sampling. We take a sample for an amount of time. And that sample only tells us between 1 o'clock in the morning to 1 o'clock in the morning, or it only tells us for 5 days that I have benzene. And if I have that benzene, I get one data point. And that data point may be 10 ppm. I don't know if that was from one release or if it occurred all day. Once again, 3 to 5 days prior to receiving your analysis from the laboratory. And finally, power is required. It has to be put in at every site. All right, and our last technology that we're going to discuss. This one's going to be a bit more involved. I think I have a few more slides in here. Because this is truly, in my feeling, where the market and where these measurements are going. And this is some of the highest level data we can get outside of the laboratory condition. These are field deployable gas chromatographs. I put with specific detectors and active sample management. I will talk both about the specific detectors as well as active sample management. In the US and Europe, mainly we refer to these as auto GCs. These products will allow for unattended sampling. That means you don't have to have someone go pick up a filter. You don't have to have someone mail that filter to the lab in order to get your results. It takes care of everything and gives you the result in the field. The measurement analysis, typically we sample and measure in a time frame. And that's every 15 minutes to every 1 hour we will give a concentration. And I did put my note that depending on the number of compounds being analyzed. This is gas chromatography. As such, we need time to separate these compounds prior to analysis. And this is one of the limitations. We don't have the ability to run multiple columns and multiple detector types typically in the field. So we are within the limitations of the operating of the gas chromatograph itself in terms of the columns, as well as the sample management system. The nice thing, we very infrequently have to go to these types of analyzers because we go in through a cellular data network, a DSL network, or a telephone network. We can control and work with our systems remotely. We can be in the United States and control a system in Antarctica in real time through a satellite link. Let the networks work for you. Getting people to some of these sites that are very remote is very difficult. So having the ability to run these systems and to have them validate and to tell you if they're running okay is very important. Systems are set up to run autonomously. What I mean is, these systems go through and they do not need a lot of hands-on or personnel time. We don't have to change the filter. We don't have to set up sample run times. They take care of the scheduling inside of the system. They allow the system to run multiple samples from different areas. They also calibrate themselves. So we put reference standards at the sites. These reference standards will be automatically run by the GC, either because it's the time to do it. Say we want to run our reference standard every 24 hours. Well, the GC will automatically run it every 24 hours. But that may not be all we're concerned with. At the same time, GCs are sensitive to the condition that they're in. They need to be in an area where the temperature does not change quickly, or there's not too much humidity. So if they do exceed temperature or humidity, they will calibrate themselves. They also perform their own base sensitivity adjustment from the calibration. So if the environment has changed around the GCs, they will now automatically accept that change and compensate or allow the unit to change how sensitive it is for the environment. Also, error reporting. Basically, if the GC fails, if we run out of gas, it will tell us that we've had a problem. What is chromatography? This is a very basic explanation of it. But really, chromatography is the separation of compounds by use of a column. And I use the term column because I'm speaking specifically about ambient air. For ambient air sampling, these columns are typically metallic. They're metal columns. This allows us to have a long life. The columns are relatively non-polar. We don't have the QA procedures in the field that the laboratories have. So by having relatively non-polar columns, they can be remotely cleaned much easier. We can get compounds to clean off of the metallic column easier, or the metal column. And then we also have the column temperature, which is critical in chromatography. The temperature, the material of the column, the polarity of the column, all play an important role on how quickly these compounds travel through the column. They typically have a precision heater on it, And since we're doing a high time resolution on some, we don't have single set point temperatures on these column ovens. We use a gradient. Basically, we ramp the temperature to separate the compounds that we need to measure. Common detector types. These are the first two. Well, it's ranked by how popular they are. First is a flame ionization detector, FIDs. Those are the most popular detectors for ambient air analysis of VOCs. Second are photoionization detectors. These are not nearly as popular. Maybe for every 100 GCs, there will be 30 to 40 PIDs. And then finally, what we have done is we have combined flame ionization detectors with mass spectrometers. And this is a very important one that we'll talk about, because we use the mass spectrometer in a non-typical way. But quickly, flame ionization detectors, how do they work? What we do is we have detection of ions formed by combustion in a hydrogen flame. The ions that are collected are proportional to the amount of the VOC present. Once again, if we have benzene and we have one ion, we know it's one concentration. If we have 100 ions, we know it's a different. And those are linear measurements on our ranges. Second, we have photoionization detectors. And this is the detection of ions from the bombardment of high energy photons. Basically, it's really bright UV light. And we have it controlled in what we say is this 10.6 electrovolt range. And what happens is that light excites that molecule, and it causes the VOC to then give off an ion. That ion generates an electric current, and that current is proportional to concentration. PIDs are great. They don't have flames. But we also know that proportional to concentration is in a very limited range. We are not able to measure from 1 ppb to 100 ppb. We may have to measure from 1 ppb to 30 ppb. And last is an FID plus mass spectrometer. What we've done with this is we use the same principle of the flame ionization detector. We have this with a gas chromatograph for separation. So we're not doing a mass spec analysis where we put a large amount of gas on and look for either total or a select ion profile. And quickly, a mass spectrometer does its analysis of a spectra caused by ionizing chemical compounds to generate charged molecules or molecule fragments and measuring their mass to charge ratio. It's another tool that's at our disposal. Sampling. This goes into how do we take the ambient air from wherever we're measuring to the instrument itself without changing that sample. And what we've got is our air sampling is performed using an inert sampling system. Basically a non-reactive. It will not change the sample. And typically this is glass or the they say passivated deactivated stainless steel. This is coated stainless steel where iron cannot come in contact with the gas. The sample travels into the instrument and then is collected onto a trap. The trap contains a carbon or synthetic media known to collect the VOCs of concern. Similar to the passive samplers that we have sampling tubes, this tube runs, collects our sample, and then allows us to do our analysis later. The trap is maintained at a specific temperature to effectively and efficiently collect the VOC. Measurement. So we've got our sample from the ambient air to the GC, and now we need to actually measure what is there. What we do is we heat the trap, to a temperature that releases the VOCs from the trapped material. Once we're heated, we put carrier gas onto the trap, and that flushes the trap, or just pushes our carrier gas, typically hydrogen, across the trap, forcing those VOCs onto the analytical column for separation. The VOCs reach the detector and are analyzed. In gas chromatography, we have some benefits. We have much higher time resolution data. That data can be, as I said, 15 minutes to 1 hour. We have very low detection limits. So I'm not sure to define it as lower detection limit or method detection limit. But either one, you're below 50 parts per trillion, and that's on the difficult. Most compounds will be 10 to 20 parts per trillion as a lower detection limit. These systems allow you to do long-term trend data and is more complete. In most of the systems that are running with the EPA, you're getting a minimum of 24 data points per day. Well, 23 minus the calibration for 1 hour. In some systems, you're getting 48 data points in a day. And I've seen up to 96 data points in a day. This tells you a lot about how those VOCs were present in the ambient air. Also, the transport considerations of active or passive are eliminated. The reactivity in the canisters is eliminated. And laboratory bias is eliminated. The downside, these are expensive systems. We are well over $100,000 to deploy most of the platforms for a wide range of pollutants. The environmentally controlled enclosure is required. We have to control temperature. And we are also having to have power at these sites. Conclusions, and then we'll move on to questions. VOCs are an important part in the understanding of atmospheric chemistry and their effects on human health. To gain an understanding of VOCs, we must first understand our objectives and goals. And this is something I didn't touch on in the presentation. We must know what the reason for the sampling of those VOCs are. Do we need to get a sample because there's a spill of a chemical? Is that the concern? Do we need to get a trend because we know that we're in a valley and that valley may not flush with air daily and we have these VOCs that continue to be at ground level? Do we need to measure an industry or a company because they don't have a spill, but they have to process these chemicals? And in the processing, they do have VOCs that come off site. Or we have a pristine, a beautiful area, a beautiful park. And coming into that park or going out of that park, we may have a reason to say, well, we don't need those VOCs, or there may be a condition where there's too many VOCs coming in. Or something as simple as, we have a lot of pine trees in this park. And we know that some of the compounds that come off those pine trees will affect the ozone concentration in the valley that's downwind. And then finally, the goal of any monitoring initiative should be to collect the most representative and defensible data possible. When we go into the field and we collect these samples, there are lots of consequences that go along if what we do is incorrect. These can be very expensive, both on industry and on us personally. So we need to make sure that when we collect these samples, we're not changing the sample, we're not adding to the sample, and that we developed a chain of paperwork that shows that when we've done this, when we've collected, we've sampled, and we've analyzed, that we know, and we've been in control of these samples the entire time. So I do appreciate it. I think that's about it. We're to the questions, but thank you all. I appreciate your time.
Las preguntas en español.
Claro que sí, yo las voy a traducir para Thor, para usted, para que él las explique.
Pero si quieres preguntar en inglés, no hay problema.
¿Qué es el pregunta en inglés?
¿Cuál sería la pregunta?
¿Me puede decir de forma específica cómo se produce qué necesidad de microscopio a partir de los recursos bioquímicos?
¿Cómo se producen los POCs?
A partir de los recursos bioquímicos.
Would you be able to tell how POCs are produced by the biotechnic sources?
To a limit, we know things like alpha and beta pinene and liminin, and we know that from sources like pine forests that we can attribute not a VOC, but a ratio of those VOCs to ground level ozone formation. So yes, as long as we know what we're looking for and we know the goal at the beginning.
¿Alguien más?
¿Y la traducción?
Es la traducción de la...
¿Nos quiere ayudar con la traducción?
Claro que sí, no sé.
Pero yo lo voy a preguntar en inglés. At the beginning of the conversation, you were talking about that Ecuador has lots of volcanoes. So I'd like to know if is there any technology that people could get, or for example, to say a cheap technology that everybody could get to know about the effects of, for example, talking about volcanoes. There will be an accident, or there will be dust before it explodes. And if there any cheap technology that people could get to know about this effect, I don't know.
You're looking to predict if there would be an event?
Yes, to predict the...
Yeah, and some of the technologies, they are GC platforms that are there. And what we do is we look for an increase in H2S concentration, we look for an increase in SO2 concentrations, and that can be tied in to predictive, as long as you look at other seismologies and other techniques for measuring these things. Then yes, there are pollutants that we can look for specifically, and that groups like the United States Geological Survey look for when they're predicting that there may be an event. But for personal monitors, if you're looking for something to hang close, no, nothing.
No sabía qué responder.
¿Alguien más?
¿En español? Si ellos... en inglés. Es decir, que ellos utilizan programas de modelación para estimar o cuantificar los COPs en general.
He's asking me about if we are using the modeling software to predict the amount of VOCs.
There are several packs of, whether it's AirMod or some of the other commercially available software. Typically those software packages will be used prior to citing the continuous GCs because of the expense. So they will validate with the canister. They will use a modeling program to predict what those concentrations may be. That program looks at ambient air data as well as data from the factory to say I have these compounds, and then it will estimate what those concentrations are. Typically they're plus or minus 50% at best. from the modeling software.
¿Con qué frecuencia se realizan los muestreos para estudios específicos o avanzados en una estación o estos son realizados automáticamente ya por los equipos que están implementados en cada una de ellas?
Esa respuesta te la voy a dar yo. Esa respuesta dijo que había 3 métodos para medir VOCs. Estaba el activo, el pasivo, medición directa. Ya con las nuevas tecnologías, en este caso los cromatógrafos, ya son mediciones directas. Esas mediciones directas pueden ser hasta 24 muestras diarias. Dependen los componentes que uno quiera analizar, los compuestos de los volátiles orgánicos, en este caso los VOCs. Las estaciones son automáticas, totalmente autónomas. She was asking me how often nowadays with the new technology, how often they're doing measurements for VOCs. And I explained to her nowadays it's like it's automated.
Yeah.
¿Cuál de estos equipos de muestreo son los que más son pedidos en el Ecuador, digamos, los más demandados aquí en el Ecuador?
He's asking me about what is the most demanded equipment here in Ecuador for measuring VOCs. It's quite difficult to answer that.
It's an emerging measurement. So I think that in Ecuador, from what I've seen and what I've learned, it's an all of the above approach. These simpler, more basic, lower cost samplers give you a lot of data, and they allow you to begin to understand what the VOCs are. And then that data can be used to make a more precise monitoring network. So there's not one piece of equipment. There's to go into a monitoring station that would be used to monitor a city like Riobamba or Quito would probably contain 15 separate analyzers to look at many different compounds to understand how those compounds affect the environment.
Para agregarle a tu pregunta, la experiencia que tenemos en la venta de instrumentación aquí en el Ecuador, la mayoría de institutos, laboratorios o ya sea agencias estatales adquieren las tecnologías pasivas y las activas, ya que lo más común, la tecnología que has visto de la cromatografía ya para llevar a campo es nueva, es muy nueva, todavía no ha sido conocida acá. Esperemos con ese tipo de conferencias ustedes puedan pasar información a dichas autoridades.